What kind of lens do we have up on the board right now? We can call it two different things. They both mean the same thing. One one name that we assign to it is called a convex lens. Convex lenses are thicker in the middle than they are at the edges, versus the other type of lens, concave, that are thinner in the middle than they are at the edges or caved in. What's the other name that we assign to this? Convex or converging. And why do we call it a converging lens? Yep. Yeah, good. All rays of light that are parallel to the principal axis. Forget about this object here right now, okay? All rays of light that are parallel to the principal axis end up converging at that spot that we call the focal point. That's a converging lens. When rays converge, rays that are parallel converge at the focal point. Now, we've got an object drawn in this particular ray diagram that's well beyond, well out there, away from the lens. In fact, the object distance, the distance from the object to the lens, is beyond twice the focal length. By the way, 2 times the focal length doesn't have any real significance optically. It's just used as a spacer when we're drawing ray diagrams so that we know exactly where our object is. Now, we're going to pretend that this object is a guy with a bald head so that lots of light reflects off of his head. And we're going to see where a couple of those rays of light go. We know that the path of those rays of light when they enter this lens is dictated by Snell's law. Sine theta 1 over sine theta 2 equals n2 over n1. We actually have 2 Snell's law things going on here as it enters the glass and then as it leaves the glass. Okay, but in the end, we don't need to do Snell's law for this because we've got 2 rays that we choose to draw here that are very predictable. We already know where they go without bothering to calculate the angles. If we did calculate the angles, we would find that this ray of light would end up going right down here through the focal point. Now, of course, the reality is it actually bends as it enters the lens and then bends again as it leaves the lens, but the net effect is this. It ends up going through the focal point. The second ray of light, we're going to say reflects off of this bald guy's head. It's going to go down right through that point that we call the optical center, the geometric center of the lens, and it's going to keep going straight through. And once again, we know it actually bends a couple of times, but in the end, the net effect is that it ends up going straight through there. Where's the image formed here? What do we end up seeing as a result of this lens? We draw the image right there. Our object starts at the principal axis. Our image starts at the principal axis. Our object ends where the rays start. Our image ends where the rays converge together or come together. The characteristics or the attributes of this image are, number 1, we would say it's smaller. You can see that red line, the image is smaller than the object. We would say it's inverted or upside down. Sometimes you see different terms for this, but they mean the same thing. Inverted, upside down, flipped over. They all mean the same thing. 3, we would say that it's real. Real means that it can be projected onto a screen. Like the Canada flag that we did in our demonstration yesterday could be projected onto a screen. In fact, we did project it onto a screen. Just because we can doesn't mean we have to. We'll still call it a real image even if we don't see it on a screen, but we can project it onto a screen. Versus a virtual image that even if we want to, we couldn't project it onto a screen. You go into the bathroom in the morning, look at your face in the mirror. You can't project that face onto the wall behind you or onto any kind of screen. You have to physically look into the mirror to see it. That's an image, but we call that a virtual image because it can't be projected onto a screen. When we draw a ray diagram, we know we have a real image when solid lines intersect. It's a virtual image when dotted lines intersect. So this one is smaller, inverted, and real. Let's skip forward a couple here. This time we have our object right at the focal point. First ray is going to bounce off the guy's head down through the focal point. Second ray is going to go down through the optical center. And we can see when that happens that these 2 lines look to be parallel. Even if we extend them back, they're not going to intersect anywhere. Because of that, we would say in this case there is no image formed. Not only could you not project that onto a screen, if you physically look into the lens, you would not see an image. Now, that doesn't mean you couldn't put a screen here. If I put a screen right here, what would I see? Nothing? No, I'd see something. I just wouldn't see an image of the person the man that was standing there in front of the lens as the object. What would I see here? Light. I would see just blurry light. Light goes through a lens. Whether it forms a perfect focused image or not, it goes through the lens. In this case, again, we just see this blur of light on the screen in that range. No recognizable picture or image whatsoever. Let's go forward one more. This time our object is really, really close. It's inside the focal length. First ray parallel down through the focal point, second ray down through the optical center. They don't converge on the right-hand side, so let's extend them back. We're going to find that they converge over here on the left-hand side. Our object starts with the principal axis, so does our image. Our object ends where the rays start. The image ends where the rays come together. We would say in this case that the image, the red image compared to the black object, is larger. We would say that it is upright. And we would say that it is real or virtual. Emma? Virtual. Virtual means that we cannot project it onto a screen. If we want to see it, we've got to physically look into the lens to see it. Here's your object over here. Let's stand right here, look into the lens. As we look through the lens, we see the image of the object back here. It appears to be behind where the object really is, and it appears to be bigger. Okay, our eyes and our brain are tricked into thinking that we're into seeing something that doesn't really exist as we see it. Just like when we had that pencil in the water and the pencil appeared to be bent, our eyes and our brain were tricked into thinking that the pencil was bent, even though we know it was an optical illusion. That's exactly what we have here. Okay? It just happens to be in this case, not bent, but rather magnified to appear bigger. All right? This is the magnifying glass, right? When you put a magnifying glass really near the object that you're trying to magnify, like we have here, then we produce an image that's right side up and virtual. We got to look through the lens to see it, and it's going to be bigger as well. And it appears behind where the actual object is. Now, we did 5 more ray diagrams yesterday. That's what we finished class off with. This is our concave lens, our caved-in lens, also known as a diverging lens, because the rays of light here diverge away from a focal point. Parallel to the principal axis, they diverge away from that point. Another one, it diverges away from that point. Rays parallel to the principal axis diverge, hence diverging lens. Now, for this one, we draw the first ray parallel to the principal axis, and then it diverges away from the focal point. The second ray is going to go down through the optical center, and it's going to keep going down through the optical center. Now, if I extend that one backwards, like I did yesterday, you would see that 2 dotted lines intersect right there, which means that this is a smaller image. The image is smaller than the object. It is upright, or right side up, and it is virtual. In other words, in order to see this, you got to physically look into the lens. You can't project it onto a screen. I had you draw the other 4 yourself. They all end up being pretty much the same. I'm going to skip forward and draw one more for you, though, just to make sure that you guys were on the right track yesterday. Now we've got the 2 extremes, right? We had our object well beyond 2F. Now our object is inside of the focal point. First ray, parallel, and then it refracts away from the focal point. Second ray, down through the optical center. Our image is formed right here. Same 3 characteristics as we just had. It's smaller than the object, it's upright, and it's virtual. Now, if you take a look at this one versus this one, you can clearly see the size has changed, but it's still smaller than the object. Its placement has changed, but it's still in the same vicinity. It's the same type of image, it's virtual, and they're both going to be upright. Okay, and that's going to be the case every single time you have a concave or a diverging lens. Today I want to spend a little bit of time doing some math on this. There's 2 equations that describe curved lens math. One we call the thin lens equation. The thin lens equation looks like this. 1 over F is equal to 1 over DO plus 1 over DI. F is the distance from the lens, from the center of the lens, that is the optical center, or the geometric center of the lens, to the focal point. DO is from the center of the lens to the object, and DI is the image distance from the center of the lens to the image. The units that we use for these are a little bit different than what we're used to seeing. Meters works, and meters are the standard units, but usually we don't see problems involving meters. Because we have a distance on the bottom in all three terms, it actually doesn't matter what units we use. We can cancel them out. We usually end up seeing centimeters, and it's okay to use centimeters here because the units end up canceling out. If you're not comfortable with that, if you'd rather use meters, then use meters. That's fine too. But because the units cancel, we can get away with sticking with centimeters, and we usually end up seeing centimeters in these questions. Now, the other equation is called the magnification equation. HI, the magnification is HI over HO, and it's equal to negative DI over DO. DI is the image distance from the lens to the image. DO is the distance from the lens to the object. HI is the image height. And HO, of course, is the object height, how tall the image and the object are. M, the magnification, is the size of the image relative to the size of the object. In other words, how much bigger or smaller the image is as compared to the object. Every mathematical question that you get involving lenses is going to involve one or both of these two equations. The tricky part of this is not the equations themselves. The tricky part of this is the signs that go with them. Okay, each of these variables, F, DO, DI, HI, HO, and M, each of those 6 different variables can be positive sometimes and negative sometimes. And we have to keep straight when they're positive and when they're negative. So I'm going to write down a little chart here to help you with that. When is DO, DI, and F positive? Well, you have a positive focal length if you have a real focal point. Can anybody tell me when you think you have a real focal point? In what situation would the focal point be real? The focal point is real when the rays really go through there. This is a virtual focal point because the rays diverge away from it. That's a virtual focal point or a negative focal point. This is a real focal point because rays that are parallel to the principal axis really converge there. So we're going to say that F is going to be positive. F is going to be positive when we have a real focal point or whenever we have a converging lens. It's going to be negative when we have a virtual focal point, and that's going to be when we have a diverging lens. So keep that straight. Every time your lens is converging, make F positive. Every time it's diverging, make F negative. Sometimes you'll be given a number for the focal length in a question. It'll just be given to you as a positive value. But if it's a diverging lens, you got to make sure that you make a negative value. When is DO positive? Well, when you have a real object. And it's negative when you have a virtual object. The good news is for you guys in Physics 30, the object will always be real. And it will never be virtual. Now, it is possible to get a virtual object. It just won't happen to you guys in Physics 30. If you go on in physics, take another course in physics, or take a degree in physics or engineering, then you will see situations where the object is virtual, but that's just not going to happen here. It would require a 2 or 3 lens system. So the image from one becomes the object for the second lens, like a telescope type thing. That's when you can get a virtual object. But for you guys, that won't happen. DI, when is it positive? When you have a real image. And it's negative when you have a virtual image. Now, you know that you always get a virtual image with a diverging lens, and you sometimes get a virtual image with a converging lens. So DI, we can't really give any more clarification on when it's going to be positive and negative. You got to look at each individual situation. If it's real, make it positive. If it's virtual, make it negative. Now, HO and HI, the image height and the object height, I'm going to color differently just so that you can see a little bit of a different trend here. HO is positive, not because it's real or virtual. HO is positive if it's an upright object. If the object is right side up, and it's negative if it's an inverted object. The vast majority of the time, your object will be right side up. If it doesn't say otherwise, just assume that the object is right side up. HI is positive if you have an upright image. And if you think back to your array diagrams, you know that you have an upright image whenever the image is virtual. If you have an inverted image, and you get an inverted image whenever it's real, then we're going to make HI a negative value. And finally, M, the magnification. I always put this outside of the table because it doesn't really fit with the other ones. M is positive if the object and image are on the same side of the principal axis. In other words, if they're both upright, M is positive. If they're both inverted, M is positive. If one's upright and one's inverted, M is going to be negative. So a magnification of +1 means the image is the same size as the object, and they're both on the same side of the principal axis. If the magnification is +2, then the image is twice as big as the object, and they're both upright. If the magnification is -2, then the image is twice as big, but the image is flipped over. If the magnification is +0.5, then that means then the image and the object are both on the same side. They're both upright or inverted, but the image is smaller. It's only half the size of the object. When you're doing problems with this today and tomorrow, make sure, please, that you have this table handy. Be looking at this table. It's okay to look at this table when you're doing problems. When you have a quiz or a test, you can't look at it, right? But while you're practicing, thank you. While you're practicing, it's all good, right? That's why we write it down, is to refer to it. Don't go home tonight and say, oh, I got to work on these problems. I got to have that table memorized. No, you don't. You have to have this table memorized for quiz day, not for tonight. Look at the table, and honestly, the best way to learn the table is to use the table, to use it when you're doing questions. Yeah. All right, we're going to do one example. This one's actually out of your textbook, as opposed to an example that I made up myself. So I'm not going to photocopy this for you. You guys just can reference it in your notes. Say example 13.7, page 681. It says a 2.5 centimeter high object is placed 10 centimeters from a diverging lens of focal length 5 centimeters. What's the image distance, the image height, and the attributes? The attributes are just the characteristics. We're not going to bother verifying our answer with a ray diagram because we've drawn all the possible ray diagrams already on that template that I handed out yesterday. What do we got here? A 2.5 centimeter high object. We're going to make that HO. HO. And it doesn't say whether it's right side up or upside down. So we're just going to make it right side up. By default, right side up. Therefore, it's positive. It's a diverging lens of focal length 5 centimeters. I think that's all we have. Is everything right here so far? Whenever you get one of these questions, it's a good idea to right away circle what type it is, diverging or converging. If it's diverging, then that means the focal length is -5, not +5. If you miss that, you will get this question completely wrong. That one small thing makes everything in this question wrong. All right. Sorry, we got one more thing here. We got DO, right? DO is 10 centimeters. And it's positive because DO is always positive for us. It's always a real object. We want to find the image distance, DI. We want to find the image height. And we want to find the attributes. We'll worry about those after we calculate those two numbers here. Here's what I'm going to do. Let's solve for DI first, and let's use the thin lens equation to do that. 1 over F is equal to 1 over DO plus 1 over DI. 1 over -5, not 5, is equal to 1 over 10 plus 1 over DI. How many of you guys feel like you're good with fractions? The good news is you don't really have to be that good with fractions in these questions. There's a little trick on your calculator that we can use. Look very carefully here. Watch carefully what I'm about to do here, okay? I want to take the 1 over 10 over by subtracting, right? And then I want to flip everything over. So here's what I'm going to do. I'm going to say -5 x to the -1. That's 1 over -5. Subtract 10 x to the -1. 1 over -5 minus 1 over -10. The 1 over 10 comes over by subtracting because it's added on the right-hand side. Equals -0.3. Well, that's not DI, that's 1 over DI. So I'm going to hit x to the -1 again to get DI, and my answer works out to be -3.33. Which rounds to 2 digits, -3.3 centimeters. I was able to use centimeters because units cancel. Okay, I chose to do that. If you want to use meters, you can go ahead and do that. See what I did, guys? 1 over 5 minus 1 over 10, and then I had to flip it over to get DI. -5 x to the -1, subtract 10x to the -1, flip it all over, done. That's a lot easier than finding a common denominator, I think, isn't it? Which is what you'd have to do if you're doing it by hand. All right, let's find HI. We can say HI over HO equals -DI over DO. This is what comes from the magnification equation. HI, one second here. HI is what we're looking for. Let's just finish this up. It won't be long here. Over 2.5 equals negative 3.333 over DO, which is 10. Let's say negative 3.33 divided by 10. Multiply that by 2.5, we get an image height that is 0.83. Okay, let's look at the attributes here. And then we're done here, okay? Attributes. What do we know about this? Larger, smaller, same size. The object is 2.5 high. The image is 0.83 high. Is it larger, smaller, same size? It's smaller. Is it upright or inverted? The image height is positive, so it's upright. Is it real or virtual? The image distance is negative, so the image is virtual. Does that make sense? Good there?